traffic data, how Mapbox actually creates global traffic data from our massive data adoption. And with me here today to help explain it are Saba El-Hilo and Rogero Taki.
Hi, everyone.
So we're going to do 4 things in the session today. First, we're going to talk to you a little bit about why Mapbox has created traffic. Why do we think this is an exciting problem to attack, and what value we think it'll create in the world? Second, we really believe that the key to our traffic is massive data adoption. And to deal with that massive level of data, we had to create a telemetry pipeline that can deal with it. So Saba is going to walk you through what that telemetry pipeline looks like and how we've tackled some of the big challenges in big data. Third, we have an interesting approach at Mapbox to both measuring traffic quality and continually improving traffic quality with machine learning algorithms. Rogero will walk you through how our traffic continually gets smarter by feeding more and more data into machine learning. And finally, I'll talk a little bit about how we actually use Mapbox traffic, how you can use it, whether that's through an API, a data set, or a turn-by-turn navigation experience. So let me first talk a little bit about why we've chosen to attack the problem of traffic. Why is this an interesting thing for us to solve? It comes down to one simple fact. Our customers are increasingly demanding real-time accuracy because they're running real-time businesses. Whether that's a business that's doing ride sharing or ride hailing in real time, or whether that's a business that's trying to do delivery with just a few minutes of leeway each way, our customers are asking for the most accurate traffic data on every street in the geographies where they operate. Let me give you a few examples walking you through how people actually are using Mapbox traffic data today. So first, I want to talk a little bit about Instacart. As you probably know, Instacart is one of the largest delivery services in the United States, focused on delivering groceries within really a couple hours of you placing an order to having groceries show up on your doorstep. Instacart's using Mapbox traffic to power their entire fulfillment pipeline. What that looks like is they have an internal system which is using our traffic to find the optimal delivery route, to assign the correct shopper to the right delivery, and to then guide that shopper to your doorstep so they can drop off the groceries. Instacart's also using Mapbox to power all of the ETAs and customer-facing items on their website. So when you see a driver approaching, that driver's ETA is actually powered by Mapbox traffic. Instacart has shared publicly that one of their biggest goals is actually increasing the utilization rate of their shoppers and be able to increase deliveries per hour. They see Mapbox traffic as one of the key capabilities to helping them get there. Another example in the on-demand delivery space is a company called Saucy, which does on-demand alcohol delivery. Their goal is to get you alcohol to your doorstep in 30 minutes or less. It's what they call the liquidity premium. And they have actually been working with Mapbox traffic for a couple of years, ever since we started the system. And as we continue to add more and more data and refine our traffic algorithms, they've been able to see their own deliveries become more and more optimized as well. So they've been able to actually cut average delivery time by more than 15% since they started using Mapbox traffic, which, as you can imagine, if you're ordering alcohol for this, your party tonight, is pretty important for their business. Favor is another on-demand delivery company, which is more in the food delivery space. They have more than 50,000 drivers across more than 100 cities in Texas. Favor is using traffic data to power their own routing engine. What that means is that they're using our raw data set. They have a custom routing engine, and that routing engine powers everything from driver matching to customer ETA prediction to actually optimizing the way that orders are delivered and the sequence to which they're delivered. On the consumer side, you have more of ride-sharing or ride-hailing companies like Belka.car. So Belka.car is actually Russia's leading ride-sharing company. We think that traffic in Moscow is actually pretty tough to predict and pretty bad, but Belka.car uses Mapbox traffic data to be able to actually match customers to the right car and improve the overall optimization of their fleet to get their utilization numbers up. That translates directly into their bottom line with the most accurate live traffic data. Finally, we do have, of course, customers that aren't doing on-demand with Mapbox traffic. One that we can share publicly is LlamaSoft, which is one of the largest supply chain design companies in the world. LlamaSoft is really focused on helping large companies optimize their supply chain and help them achieve as close as possible to a lean manufacturing system. So very large companies like GM and Adidas actually work with LlamaSoft to help predict exactly when the delivery will get to the factory, so that they can optimize the order of deliveries and figure out their overall supply chain optimization. Now I'll hand it over to Saba, who will tell you a little bit more about Mapbox's data, what that looks like, and how we process it.
Thanks, Ben. So at Mapbox, we refer to all the data that's collected from mobile devices as telemetry. So these are mobile devices that are running Mapbox applications. So I'm going to talk through how we go from telemetry data to the final data set of traffic. There are 45,000 applications worldwide that use Mapbox and maps and services. So this ends up being, on a monthly basis, we have more than 600 million active users using our maps for a wide and diverse range of use cases. And this usage actually allows us to collect more than 300 million miles of telemetry data per day. So this is a lot of telemetry. Let's take a look at what telemetry looks like on a map. At the fundamental level, a location data point can be called a probe. And what a probe is, it's a data point that contains latitude, longitude, and a timestamp. So here we have a map of downtown LA where we plotted like a bunch of probes on it. And these probes are visualized according to deceleration. So the brighter and bigger the bubble here that you're seeing, that means the driver is actually moving slower. So from this map, we can actually start to derive some pretty cool insights. Like you can tell that everyone is driving on the right side of the road and that there's a traffic light at the intersection because everyone's coming to a stop. But you can also see that there's a lot of activity around one of the buildings. And we actually know that there was a conference that day and cars are driving in, dropping people off, and then driving off again. So some pretty cool insights from just location and like probe data, which is just latitude, longitude, and timestamp. So what happens when we connect a bunch of these probes together? Well, we end up with something that we call a trace. So a trace is just simple. It's just a series of probes that are connected together in a sequence. And this map here is of LAX airport. And the traces are visualized here and color-coded. And you can see how things start to get even more interesting than just visualizing probes. You can start to understand driver behavior and see some patterns in the data. So here you can see that people who are driving into the airport have different driving behavior than people who are driving out, especially like those loops that are happening in parking lots where people might be waiting to pick out someone from who's arriving to the airport, or just looking for a parking spot, or people who are leaving the airport just drive through continuously and out of the airport. So we talked about probes and how these can be connected into traces. The third level of information that we can derive from this is speed. So this map here, we have traces visualized by speed. So the brighter the color, the faster these traces are moving. And again, you can start to see some pretty cool insights and data here. You can see how speed varies within like lanes and how people exiting the highway are slower than people driving on the highway. And so on. So yeah, so this is the third level of information that we can derive, which leads us actually to like the traffic data. As I mentioned earlier, we collect all of this telemetry data from mobile devices that are running applications that have Mapbox. So the location manager on these mobile devices can collect this data from three different ways, either from GPS, network, or cellular triangulation. So this data is actually inherently very noisy, as you probably know. And here we have data, telemetry data that's visualized before it's been cleaned up, before it's been pre-processed. And you can see how there's a lot of noise. But you can also see how that there's underlying signal in this image. So that's why we've invested so heavily in like our machine learning algorithms and classification models that can clean up this data really well and produce this beautiful image of like high quality signal and really high quality telemetry data that's basically from mobile devices. So at the end of the day, we want to produce a data set like this. So a traffic data set where you can easily visualize how fast or slow people are moving in a city like New York. So now we know how we can get from telemetry data to traffic, but how do we actually do that? Like, how do we generate this data? And how do we deal with the large scale of data volume that we get every day, like 300 million miles of telemetry data? How do we process that and produce it as a traffic data set that we can provide to customers? So telemetry events are continuously coming in from mobile devices with applications that use our telemetry SDK. All of these events come in and they're put through a rigorous anonymization process, and they're classified as driving, and then we end up with these beautiful traces that are anonymized and then we call like driving traces. From these traces, we can actually estimate the speed based on the consecutive coordinates like within these traces, and that final result we refer to it as a speed probe. So now you have distance, duration, heading, and speed information from the original just longitude and latitude. We take anonymization and user privacy very seriously at Mapbox. So for all of the individual location data points that come in, so longitude, latitude again, we aggregate them and then we segment them into shorter chunks. And the purpose of this is to ensure that we don't have any continuous user trips from beginning to end stored in any of our databases or downstream processes. And then further, from these chunks, we actually end up dropping a random number of data points from the start and end of each one of these chunks to protect user privacy even further. So we drop all personal identifiable information, and we actually end up dropping 10 to 15% of our data per day to ensure that the data is completely anonymous and that user privacy is protected. Okay, so now that we have discrete probes, what do we do after that? So we aggregate them and we actually match them against the entire world's road network to come up with one number. So we want one speed estimate for every road per 5-minute time interval for every day of the week. You're probably thinking that must be a lot of data, and it definitely is. So on a weekly basis, we match something like an upwards of 1 terabyte of traces against 200 gig road network to produce 2 terabytes of what we call a traffic profile. So how do we do this? How do we churn through these massive amounts of data? There's 2 aspects to it. So we have the live traffic aspect and then the typical traffic aspect. So live traffic is basically real time happening from location data that's arriving right now, and you're producing a speed estimate in real time. Whereas our typical data is based on historical observations that could span multiple months. So for our real-time processing, our pipeline performs processing on the stream in real time to produce a speed estimate, as we said, in real time. So we have all of these location events coming in on an Amazon Kinesis stream, and then we have thousands of processes running concurrently that take these events. They anonymize, classify, all on the fly in real time, and then match against a cached road network, again in real time, to produce a live traffic data set. On the other hand, typical traffic is a little bit different because we're dealing with a lot more data, because we might want to look back several months in a certain area to come up with a speed estimate for that road. So the data becomes a lot bigger. So we actually take advantage of a distributed computing framework, which is Spark, and this allows us to process incredibly large data sets really quickly and efficiently. And then we use Airflow to manage all of our pipelines and orchestrate all of these tasks that are all running on a distributed cluster that can be like magnitudes of like hundreds of nodes at a time. So it comes with like what has been like the biggest challenge when it comes to processing location data. I have to say it's data skew. And what we mean by data skew is when your data is not distributed evenly across partitions or a heap. And this happens a lot with telemetry data. As you can see in this histogram graph, there's one location where there's significantly more data than anywhere else. So you can imagine if you're trying to process this in a distributed fashion, you're going to have some process that's going to take way longer than anything else. And you're basically not utilizing the resources to the fullest extent. So for all of our data, we actually have to repartition it before we do any processing on it to ensure that it's evenly distributed and that we can, take advantage of the infrastructure that we have. I'm going to hand it over to Rogero to talk about the machine learning and the AI part of this.
Thank you, Saba. So, as you heard so far, we have a lot of data, and we are trying to create a model for traffic that achieves good ETAs and a good navigation experience. So one of the most important pieces in terms of the machine learning that we do is the very, very first piece of the pipeline, which is the classification. Our data comes from a whole set of devices, but mostly mobile phones. And so when that happens, as you can see in the image here, like people could be driving, could be walking, could be going on a bicycle, could be doing many things, running, or even on a plane if the GPS works. So it's very important for us to be able to distinguish between these cases. So our classifier learns from the behavior of these devices how to distinguish between driving or not driving, which is our most important distinction. As you can see in the image here, the color is purple for non-driving and green for driving. And you can see how most of the roads look green, but there is also a lot of roads that look purple. And the reason there is because a lot of people just walk on roads. And so it's very important for us to make sure that we don't mistake those for very slow traffic, for example. Another important thing is to see that maybe there is some green dot in places where you would not think people will be driving, like the park or the water. That is not necessarily a big deal because this is the very first part of the pipeline where, because of the massive volume, we have to be able to predict whether or not you're driving or not before we can even match anything on a map. But in the second part of the pipeline, when we'll match on a map, then we will be able to realize that that individual data point is not on the road, and so it doesn't contribute to our traffic model. Here on the right side of the slide, you can see 4 examples of how the real probe data looks like and how we help classifying them. On the top left of these 4 little maps, you can see a car that is driving on a slower pace. On the right top, you see a car that is going pretty fast. At the bottom left, you see probably a person that is simply around the square taking pictures, moving around. There is a little bit of GPS jitter. And you can see how different that signal is. And then on the bottom right, there is one that is maybe a little harder. There is a lot of GPS jitter, but it could be potentially driving and crossing, or it could be too slow and maybe it's someone more. So the massive work of labeling and understanding examples like this, and then eventually our classifier can do the work for us. So imagine now that you have all this classification done, and as you can see on the right, these are 2 examples. Now you still have, as I was saying before, something to solve. Like, for example, in the bottom little map, there is a point in which the GPS seems like it's going into the river. So obviously that's not possible. So either it's close enough to a road and we associate data on that road, or we throw it away if it's too far and we don't feel confidence. Like Saba was saying, we collect all this data and we process them in this very, very performance demanding ways. What we end up doing then is, as you can see on the left side, is some sort of association to a road. And then we basically build like all our data set. And so this is our starting point to then process and work on our traffic prediction. You can imagine that this thing happens in both situations, for live or historical. Obviously, for historical, you have a lot more data versus for live data, the quantity is sparser. Now, Imagine that now you have processed all the data, and now we have a model for traffic. The first thing we do is to compare, how do we do? How is our quality? Like, is it up to standard? So one of the things that we do to evaluate against our competitors is to check individual specific A to B directions. And in this case, there is a Clement Street to the Mission in San Francisco. And we can compare, like, oh, are we better? Are we worse? We can't use this for training, of course. This is just for measuring. But it gives us a good idea about how we do against our competitors, which is very important for our customers.
And I think it's worth mentioning that in this benchmarking, we really picked what we consider to be the best competitors. There are, of course, other companies that we benchmark against that do not produce accurate traffic for San Francisco.
Yep. And you can also think that the same methodology can be used against ground truth, and A and B become our A/B testing, not companies. So we can also map different variations of our models in the same way. And so you would see like which model performs better compared to ground truth. As you can see, we do this in multiple places in the world. We offer global traffic, so this has to be monitored everywhere. One of the difficulties, though, when it comes to this is that you don't really want to have 1 million of these routes to compare just eyeballing. So we actually have a system that does it automatically on thousands and thousands and thousands of trips a day. And specifically, I believe it's about 1,000 a minute. And so if you do that, then you can start coloring a map based on the quality of the traffic you see. In this map, I basically plotted trips that we collected. And the color scheme goes from red when our prediction was a little bit too optimistic, to white when our prediction was very accurate, and then to blue when our prediction was very conservative. And so what this helps us do is to have also a methodology to go really deep into all the streets of a city, for example, in this case, Manhattan in New York. And so you can see that there are some areas that are a little bluer and some areas that are a little redder. And that means that maybe in some areas traffic is heavier than we thought, or in some other areas traffic is lighter than we thought. While you can see that most of the freeways look relatively gray, which means that they were easier for our model to perform well on. And not naturally, you don't want to just keep looking at maps. You also have to measure things with numbers. So when you put all the trips from the previous map together, we can build metrics. And so in this specific case, you can look at some of the metrics we use. For example, we look at trips that are within 10% of our ETA, or within 20%. Then we have an area under the curve that tries to like look at every single 10%, 20%, 30%, 40%, and so on until we get to 100% trips. And then you can see also our distribution of errors. In this case, you can see that our standard deviation is probably about 15% here in this subset of data points that I chose for the screenshot. You can also have an idea about whether or not we're too aggressive or too conservative with respect to the ETA based on the shift of this plot. And in this specific case, the plot is pretty well centered and with some Billinaga artifact. Maybe it looks a little bit on the right. Now imagine that you do that for a lot of different regions in the world. Now we can start mapping it in a way that can help us understand also regional differences. So each little pixel here represents one of these previously seen distributional errors. And you can color here by green when we are very centered and when the distribution is very skinny, let's say, towards no error, and red when instead our error becomes a lot bigger. So in the specific week I chose for this screenshot, you can see that there is something probably in Oregon that was happening. Maybe there was a bigger event than we thought, or some weather event, and so it's a little bit red. But overall, the entirety of the United States looks very green, which is good news. It means that our ETAs are accurate. You can see a similar map for some selected countries in Western and Northern Europe. And in this specific example, you can see how Finland was doing extremely well. Now, an important, very important concept in traffic is live coverage. Traffic is something that can vary sometimes even in 5, 10, 20 minutes. So it's very important for us to adapt to the traffic conditions as quickly as possible and to make sure that we have a lot of coverage for areas where live changes are important. So specifically, when you look at a map, sometimes at a high zoom, it looks like not a lot is covered. But then when you zoom in, you can see how a lot of these roads are covered in terms of traffic. And some areas are red, some areas are green. In this map here, red or green means there is no traffic versus traffic. But when we actually go and look at the data underneath these maps, then we can have an idea about how much of our data is influenced by live detections. So for example, in this map of San Francisco, I plotted only the speeds of live data.
Is your volume on? I'm sure.
Are we good? Can people confirm? All right. So we're talking about live coverage. So, third time charm. Okay, we're good. So we were saying it's very important to understand the impact of live coverage. And live coverage is something that is extremely important for our accuracy of traffic and ETAs. And you can see here that the color scheme is red to yellow to green to blue based on how fast the detection is. And so it's not a surprise that San Francisco in downtown is pretty red because it's pretty trafficy. But red here also means that we actually do have data. And so that's exactly where you want data. You want data where there could be congestions and where there is a higher likelihood of having traffic conditions that are different from typical traffic conditions. In fact, you can see that on the northwest part of the map, in the map on the left, the bigger map, you can see how there is less live data, but it probably doesn't matter as much because that's probably something, there's probably a place in which nothing specifically is happening now, and so the typical traffic estimates will work. So when we move now to actually looking at the effect of this, now you can look at a ground truth collection, and then you can look at our historical baseline compared to our live traffic. So you can see how the baseline is pretty similar to the actual ground truth, but there are some differences. So some things have changed that day or those days compared to historical, because there is always a little bit of variation, especially towards the end of these few days. You can see that there is a very long spike. On the right side, as we introduce our live correction, let's say, on our models, you can see how the traffic and the ETAs become almost a perfect overlap with the ground truth. Even in extreme cases, this was an example from the beginning of February in Denver. There was a very big snowstorm and all the ETAs were suffering. And so you can see here on the graph how the typical winter average in Denver is this gray line where our typical error is between 10% or negative 10%. Then you can see how only historical data during the snowstorm was performing extremely badly because obviously it's not expecting something some weather event. It's expecting something typical, an average case. And you can see how live data improved that of at least 50%, bringing us basically to an overlap, not complete, but still pretty valuable for our customers. The increasing the error of 50% is something extremely valuable in these situations that are very extreme. So you can imagine that also what we can do to keep learning and improving our models over time is some sort of machine learning-based feedback loop. So we look at those maps that I mentioned at the beginning, in which you can see optimistic, pessimistic ETAs, and you can see where we do well. And you can train a model to learn that over time and apply a correction live so that the quality improves. So on the left side, you can see how the color blue versus red means that traffic became better because of the machine learning layer. And you can see on the top left side how even our distribution got centered better. So you can see how learning from the ground truth continuously makes our traffic better and better. So the more data we have, the more accurate the traffic becomes. The very last piece of this is also having very good incident data, because that can fix very important problems of routing. And so when the route is incorrect, also the ETA is incorrect and the traffic is incorrect. So by adding this, we can avoid all places where mistakes in terms of ETAs. And through these data sets, we improve greatly our quality. So overall, with all these sort of machine learning type of approaches, you can see here an interesting artifact, I think, of the slide, but you can see how in a few months from October through May, we were monitoring improvements in Reykjavik due to our machine learning and model improvements. And you can see here in red, green, and where we were making mistakes in red versus where our prediction was very good in green. And so you can see how over this period of about 6 months, our traffic in Reykjavik, as an example, greatly improved, especially on that weekly set of freeways that go from north to south. And then I'll pass it back to our offering.
Awesome. Thanks, Ruggiero. So now you've heard a little bit about what Mapbox traffic is, how we create it, why we think it's really high quality. Now that we're going to talk about a little bit of how you use it. And the good news is we actually offer a bunch of different options for how you can use Mapbox traffic. One of our options is a set of really powerful, low latency and performant APIs that power ETAs, turn-by-turn navigation, or optimization. Mapbox APIs you can just call from the command line, and we have a bunch of different APIs available that incorporate traffic information. So we have a directions API that will give you traffic-aware A to B routing and ETAs, helpful for just getting anyone from one point to another, and you can use that in walking, biking, or driving mode. We have a matrix API, which gives you multi-origin or multi-destination optimization. For instance, if you want to figure out feed something into a route optimization engine or a trip optimization engine, you might actually want to compute the distance between a whole set of different stops. We have a trip optimization API that solves the traveling salesman problem using traffic data for you to give you a traffic-aware list of delivery stops for anybody who needs to make a number of stops in an arbitrary order. We have a map matching API, which will actually snap points to a road network and give you accurate speeds and ETAs, often useful if you're trying to understand how someone has actually moved in the past or if you're monitoring someone's location over time. And with all of these APIs, you have the choice of letting Mapbox do the routing for you and pick what we think is the best route, or using waypoints to establish an existing route and just getting a really accurate ETA based on that. So if your vehicle, for some reason, had to follow an existing route, or you wanted to compare, say, the performance of the past vehicle versus live traffic conditions, you can do that with Mapbox. In addition to our APIs, Mapbox also offers a turn-by-turn SDK. This SDK is a software kit that you can drop into an iOS or Android application. And it lets you actually build a turn-by-turn experience similar to what you might see in a consumer app like Waze or Google Maps. Our turn-by-turn SDK has really accurate guidance. It will automatically reroute someone if they get lost. And it's really customizable. So it's built for anyone who wants to produce something in their own applications that feels like their routing experience. And of course, our turn-by-turn SDK also includes Mapbox traffic, and it will help you do traffic-aware routing and traffic-aware ETAs as well. Finally, we have a traffic data set called Mapbox Traffic Data that we can deliver directly to you. This data set actually captures all the Mapbox traffic data we were just discussing. It gives you both the live traffic that we update every 5 minutes, and it gives you typical traffic that we update weekly, but covers an entire week. So, what's Monday typically like at 12 p.m., 12:05 p.m., and 10 p.m. With Mapbox traffic data, you can actually use it as flexibly as you want. So we have customers using this for everything from routing to analytics to trying to predict urban plans. And finally, with Mapbox traffic data, you're actually not limited to using a Mapbox map. So we give you traffic data identifiers in either OSM or OpenLR, which means that if you're tied to a legacy map producer like here or TomTom, you can use accurate Mapbox traffic data with your existing map. The most common use case for Mapbox traffic data is what we call custom routing. So if you think about what the Mapbox stack looks like for something like the Directions API, there are really 3 components. On the base, you have Mapbox traffic data, which is everything we've just discussed. There's also a routing engine that actually solves the graph traversal problem to figure out where someone should go and how long it will take them to get there. And then, of course, there's a performant API layer to deliver that to you or to whoever calls the API. We understand that this is not a great fit for every customer, although it does work for most. So some customers actually want to incorporate their own data or want to build their own routing engine that's tuned for their use case. For these customers, Mapbox traffic data can make a lot of sense. What we do is we actually deliver you the raw data. You can incorporate that together with your own traffic data if you want. You can use a routing engine on top of it to produce ETAs or replicate the results of our APIs, and then you figure out how to deliver it to your own applications. So this is often something for very large companies typically that want to do something custom or interesting with their routing, not available off the shelf. So finally, we're going to go to Q&A. We really encourage questions here as we dive under the hood of traffic data. And I think we have about 15 minutes to answer all the questions we can. Okay, great. I see there are already a bunch of questions coming in. We have a question from Pedro, who says, awesome presentation. Do you have this type of data for geographies outside of the USA, including, for example, Mexico? The answer is yes. So Mapbox actually has a global user base and produces traffic data at some level for over 140 countries. That said, there's definitely a difference in quality that we feel we should share with you. So we have a publicly listed set of tier 1 countries where we think the traffic data is highly accurate, suitable for consumer experience even, so as good as anybody else, and updated live all the time. Those tier 1 countries include, say, US, Canada, UK, Australia. We have a set of tier 2 countries where you'll still see a big improvement by using traffic data or by using Mapbox APIs powered by traffic, but aren't quite as good. And then we have tier 3 and below countries. So you can check that out on our website and our documentation of where we have great traffic data. So I see a question from Jesse, who says, how has the amount of traffic data you collect changed over time? It's a good question. Mapbox traffic data has really improved over time. So just to give you a sense of how quickly Mapbox is growing and the data we collect is growing, we have actually more than doubled our data collection since even the beginning of this year. And we expect to continue growing pretty rapidly as more and more people adopt Mapbox solutions. Okay, Leslie asks, what is the source of live data? Really, the source of live data for us is all the people who are using Mapbox. So we shared that we have hundreds of millions of people using Mapbox solutions. When those people use a Mapbox solution, like let's say Snapchat, and Snapchat asks for your location, Mapbox also gets that location in anonymized form. So we don't request anything more than the application, but we get the same application data, and we can use that data to create live traffic. So all the people moving in the world with Mapbox-powered applications, that's the key source of most of our live data. I see Tibor has asked, how do you filter out erroneous location data? Rogero, do you want to speak to this?
Yeah, well, there are several ways. So what's an error, first of all? An error can be many things. It can be because the GPS the GPS is just moving too much around. It could be because the app has a misconfiguration and for some reason, I don't know, it's inverting latitude and longitude. Or it could be that it's erroneous in the sense that it's not a person driving. So there are different answers to this, but typically the most important thing to keep in mind is that we are classifying them first. So if it doesn't look like driving, for example, if it's just a lot of jitter, it gets immediately discarded. And then there is the second type of filtering, which is what we call the map matching, which is looking at the actual GPS individual coordinates and see do they basically overlap close enough to a road. And so in that case, if the answer is no, the data gets filtered out. And this typically gets rid of most of the possible errors.
Great, thanks, Rogero. Erdong has a good question. So this is talking about classification and how we actually do classification. He asks, what if the same device was walking, gets in an Uber, goes fast, gets hit with some slow traffic, then gets out of the car and walks again, will you still be able to tell when the device was walking or driving? Rogero?
Yeah, I mean, great question. This is definitely one of the hardest ones to solve, right? What I can say is that our neural network classifier can classify individual pieces of a trip. So based on how much confidence we have in each of these individual pieces, we have done some heuristics to understand whether or not we want to accept that portion of the trip as a driving portion. When in doubt, it's probably better to discard. But when our algorithms tell us that something is trustworthy, then we include it.
Great, thank you. So Enrique asks, do you predict for the whole street as one? How do you segment the street for traffic prediction? Saba, do you want to talk about this a little bit?
Sure. Yeah, that's a great question. So we don't do the matching on like the entire street and the entire world at once. We actually process the data according to location. So we break up like the entire map like in smaller chunks. And then so if there's a street that belongs in that chunk, we just take that street and then match the traces to that street in that location. So it's geographically segmented so according to what we call quad keys.
Great. Yogesh asks, data set, how much does it cost? Great question. So the Mapbox traffic data set is really designed for somebody who's an enterprise customer of Mapbox and is going to build a large implementation for it. So it is available as an enterprise plan, and pricing depends on what you're using it for, as well as your geography of interest. That said, we do think it's pretty affordable compared to many of our competitors. We also have, of course, the option to use Mapbox traffic data inside of just our APIs and SDKs, where we have a pretty generous free tier. So if you're getting started, a good choice to start with the SDKs and move to a traffic data set when you want to answer some other question or get to a really large scale. Okay. Daniel asks, thanks for the presentation. Is there a chance to get a sample of the traffic data for an exact location, say St. Petersburg, Russia, to understand the data error volume? Thanks for the answer. Yes. So there are actually two things we make available. If you just want to get a sense for what Mapbox traffic data set actually looks like, we make an example data set available in our documentation, free for anyone to download. You can download it right now. It's not up to date, and it just covers one small city in the US to give a sense for what the data looks like. But if you want data for Wilmington, North Carolina, go to docs.mapbox.com/traffic-data. I believe that's also on the resources tab of this presentation. We can also give you access to sample traffic data sets for other areas like St. Petersburg. After a conversation with our team, you have to sign an evaluation agreement because obviously it is proprietary. Alexander asks, is Mapbox able to predict when is best during the day to do a specific route from A to B based on historical and live data? Yes, we can. So as we mentioned, we have a big typical data layer that we blend together with live data to give you a sense of ETAs now and ETAs during a specific time of day. This functionality we're building out internally within our APIs, and we're scheduled to have it available by the end of the year. So you can compare, say, is it better to leave at 3 p.m., 4 p.m., or 5 p.m.? It's also something you could build today with Mapbox traffic data using that typical data layer, which contains 5-minute granularity for the whole time. Vikas asks a good question. How do you show all those million points? Could you elaborate on techniques or technology? Saba or Rogero?
Yeah, I can take this. The answer is Mapbox. Yeah, so we have tooling to generate tile sets that we visualize through Mapbox Studio and create these beautiful maps that you just saw in this presentation.
Yeah, and I'd like to add that because it's so simple, like every team just makes their own visualizations. We don't need to ask another team to build us some dashboards. It's pretty powerful.
Absolutely. So if you want to show 1 million of your own data points on a map, Mapbox is also the way to do it. Okay, we have a question from Ali to talk about what is your major data cleansing filters? Which data do you filter out? Well, I'll talk about a little bit. Certainly some of it is just data we cleanse out for privacy and anonymity. So we don't capture the beginning of a trip. We don't capture the end of a trip. We break trips into chunks. And this means that we actually do filter out data just to make sure that we cannot track a single person throughout the world. We're not in the person tracking business. We are in the world live mapping business. Other than that, Saba, do you want to talk a little bit more about how we clean our data?
Yeah, so I think Rogero touched a little bit about this. So in the processing phase, once we do the map matching, so anything that doesn't match to road, that's like filtered out. And then there's also if it's not within like certain speed threshold, we also filter it out. I'd say those are like the two biggest ones that we do right off the bat.
Got it. Okay, Spencer from Oklahoma asks, how do you handle highway construction and lane closures in the data? Do you collect metrics on how often this occurs? In my state, this is very regular. Yes, so highway construction and lane closures are really important, actually, especially in places where they're building roads very quickly. There are a couple different levels on which we capture this. So a lot of it is actually captured within our live data layer. Because our live data is consistently updating, let's say that there's a construction event we don't expect. We would actually pick that up really quickly by seeing either cars not routing through that area, or if it's a partial lane closure, we would say like, okay, great, these cars are moving more slowly than normal. We'll incorporate that into our traffic map and traffic ETAs. We also, as I think Rogero mentioned, actually source external data to capture some of the data that's really gathered systematically. So we work with providers from open data sources and also proprietary data sources to bring that data onto our map and capture things like all the planned road closures, from different city governments, states, etc. And we're actually planning on upgrading that to cover more than the United States soon as well. Okay, one other question. You mentioned for privacy, you remove the beginning and end of a trip. Does that affect origin destination analysis? Yes. Rogero, do you want to talk more about the effect it has?
Yes. So basically, there are like a couple of things to keep in mind here. There is data that we use to build traffic, and then there are metrics that we keep to understand quality. So in a metric that we understand, in the metrics we use to understand quality, we look at like potentially a fake beginning or a fake origin, fake destination of a trip, so that we can look exactly at the path with respect to the actual prediction. But also from a more like navigation SDK analysis, there are like different metrics that can record the exact timestamp of origin and destination.